Thanks to everybody, and thanks to the organizers for the opportunity of presenting this work here. So it will be a bit different in the spirit with respect to the previous one, since I'm a theorist, but not so different. And in particular, we'll try to explain some recent work that we are doing together with concerning some experimental observation of conformal field theory spectra. So first of all, I want to acknowledge the team that led especially the experimental part of the work, led by Manuel Andres in Caltech, together with Shankai, Yuan, and Richard and Luis, who are grad students and postdocs there. And I'm on the theory side, together with Jason Alicea and Stephen Naus, and we have tried to understand what's going on in CFT. So first of all, I would like to explain a bit why I've been obsessed with CFT in the last years, and I think a lot of other people. So maybe it's already clear from the talks that we had in these days that critical points, criticality, plays a crucial role when we talk about quantum phase transitions. Like, for instance, think about magnetic systems with some kind of domains where you are in an order phase, and so, for instance, you have a correlation length, so the typical size of your domain, that is usually big when you are in the order phase. And then as you approach the critical point, you have more and more domains. And what happens when you cross the critical point is that the typical size of these domains diverges. So what it means is that you don't only have like rotation invariance or spatial invariance, which is something that maybe characterizes most of the systems, but you also have scale invariance. And having scaling invariance is one of the main features of conformal field theories. And usually when, so the system undergoes this phase transition and it's described by conformal field theory, there is some kind of universality that enters in the game, in the sense that if you look at the behavior of correlation function or of the entanglement, they don't depend on the specific microscopic realization of the model that you are looking at, but they are universal. Like, for instance, if you look at the behavior of the correlation function of the order parameter, they usually decay algebraically, and here I wrote x to the minus 2 delta. So basically, this delta, this power law decay, is just fixed by the universality class of the model that you are looking at. Now, if we change a bit the set of community, like these problems are interesting for condensed matters, .mech, but for high energy physicists, for instance, we heard a lot about black holes already. I think it's this picture appeared several times. And why CFT is important here? Because there is this duality between anti-de Sitter and conformal field theory. So anti-de Sitter refers to a space with negative curvature. And what the CFT correspondence tells us is that there is a kind of dictionary between a theory of quantum gravity living in the bulk and the conformal field theory living at the boundary. So you can think that, for instance, if you have access to some CFT, to some conformal field theory, then you can also extract some information about your quantum gravity part. That I think is very nice. So it's a very nice domain where CFT plays an important role. Now, more recently, something that I've been also interested in is, let's say, applications of conformal field theory and interplay with measurements. Like, for instance, what happens to the universality class that I was mentioning before when we perform some weak measurements. How these, how these delta parameters, as I said, is universal, can be affected by weak measurements. So this is just, let's say, a very sample of topics where CFTs have played an important role. But despite the theoretical interest towards this subject, I think that there has been a lot of experimental activity also to probe some of these features of a conformal field theory. Now, just to mention a few references about these that I think fit pretty nicely in this context, I want to mention a work done around 2000, I guess, were done by Immanuel Bloch here, where basically they were able to observe a transition between a superfluid to a multi-insulator phase by changing the depth of a 3D potential, and by applying some, by reconstructing the interference patterns of their ultra-cold atoms, they were able to observe this transition from one phase to the other. More in the dynamical setting, let's say, one can also observe the Kibble-Zurich mechanism in Rydberg systems, and this was done. This was done in the group by Misha Lukin that we just heard, and in this case, basically, we have already seen this picture, I think, in these days. What one can observe is that by changing the detuning parameter of our Rydberg Hamiltonian from the disorder to the order phase, where the order can be Z2, Z3, or Z4, one can observe some signature of this criticality. Like, for instance, they could reconstruct some scaling exponent falling into the Ising universality class by looking at a transition from the Z2 disorder to the Z2 order phase. And something a bit closer in the spirit to what I'm going to present today are also some attempts to compute correlation function, pure ground state correlation function. And this was an experiment done in the group by Norman Yao, also pretty recently, where they were able to compute correlation function on a ring, so on a system with periodic boundary condition, or on a 2D square lattice. And their main idea was to introduce a sort of phenomenological length that takes into account some impurities, some imperfections present in the experiment, and then by fitting to, an exponential law together with a power law, they were able to extract some universal scaling exponent for the Ising CFT. So I mentioned correlation function, and indeed, when we think about CFT, maybe we are associated with the correlation function, with the power law decay behavior. But actually, the structure of CFT is much richer. There is much more that we can extract from a conformal field theory. And also, these features can be extracted not only the thermodynamic limit, that maybe you can think, oh, this is a critical system, so I want to minimize my finite set effects as much as possible. But there is something interesting that one can extract also in finite size. And this is possible thanks to a very nice, let me call it, program developed by Card in the 80s when he was here in UC Santa Barbara, which works in the following way. So you give me as an input your favorite critical spin chain, like for instance Ising, and then I can give you as an output a set of conformal data, where by set of conformal data I mean all the scaling dimensions of the operator of the critical theory that I'm describing. So practically, how does it work? I have a system. I put on a finite size system, on a ring, for instance, if I have periodic boundary condition or just with open boundary condition. I diagonalize my Hamiltonian, and the spectrum of this Hamiltonian takes this form. So you see, this A is just some non-universal coefficient. Then I have 1 over n scaling that multiplies exactly the scaling dimension of the operators that enter into the spectrum of my conformal field theory. And this can be extracted by looking at least at the low-lying excited spectrum, where we have a conformal field theory description of our model. So we have a set of scaling dimensions that conformal field theory is predicting. This can be also extracted from numerics. And now the question that I want to address into this talk is, what about experiment? Is there a way to extract this scaling dimension here from an experimental setting? Okay, so the plan of the talk is the following. I will first try to explain a bit better what I mean by conformal spectrum, because I think that it's useful to look at it and to be on the same page. Then I will show what are the model and the experimental techniques that we have been using, and finally we'll draw some conclusions. And feel free also to ask questions whenever you want. Okay, so I think that a very simple example to reconstruct a CFT spectrum is by just starting from the Ising model. So this is the Hamiltonian of the Ising model with open boundary condition. So it means that basically my spins at the endpoint of my chain are free to fluctuate, and I have n sides. Now, I can perform a Kramers-Vanier transformation of my Hamiltonian such that I can rewrite it with these tilted variables, where now you see this Hamiltonian lives on n-1 spins, and the first spin is pin to be up. Okay, you see there is this minus sign here, and the last spin multiplies the parity, this operator P, which is nothing than the parity of the previous chain. So you see that if we project into the even parity sector, the first and the last spins are aligned, while if we project into the odd parity sector, the first and the last spins are anti-aligned. So basically we have fixed boundary condition, which can be aligned or anti-aligned according to this parity operator. Now, the nice thing of this trick is that this Hamiltonian with open boundary condition can be easily diagonalized if we perform a Jordan-Wigner transformation and we go into the fermionic picture. So if we go into the fermionic picture, basically the parity operator simply refers to the fermionic parity, so it's related to the total number of fermions. And so at this point we can construct the spectrum. Here I'm writing down, let's say, a simplified version of the spectrum, which holds in that for large values of n. Okay, so I'm discarding subleading 1 over n square corrections. But still we can see that, for instance, if we focus on the case in which we have p equal to -1, so we have anti-aligned boundary condition. I call them plus minus. Then the way to construct the spectrum is remembering that we need to have an odd number of fermions. No? So I can act with one creation operator, or with at level 1/2 with another creation operator at level 3/2. These are all in units of pi over n. 5/2, 7/2. Then I start to have different degeneracies. Like for instance, at level 9/2, I can have C-dagger 9/2, or this combination. These two levels in this case are degenerate. And you see here, by constructing the spectrum, I've satisfied the odd parity sector constraint. Same can be done for fixed plus plus, but now with the constraint that you need an even number of excitations. So this tower here and this other tower here is just the spectrum of a boundary conformal field theory with fixed boundary condition, like up, down, plus minus, so anti-aligned, or up, so aligned. And I like this way of presenting the problem because I think it's very, let's say, natural. It's very nice to obtain it. But actually, I could have also just shown the spectrum from a conformal field theory perspective, in the sense that this spectrum does not depend on the specific microscopic realization of the model that we are interested in. So let's say this is a way in which one can derive it. It's universal. It doesn't depend on the microscopic model. Let's see now what is the model that we have access to in the experiment, such that we can access this kind of information. And the model, I don't have to introduce it again, but it's Rydberg Hamiltonian. Maybe the thing that I want to emphasize about this Hamiltonian is really the phase diagram. So you see that if we change the tuning parameter, delta, the system goes from a disorder to the order phase. And in this, along this line, we have a second order phase transition that falls into the Ising universality class. So maybe if you are more familiar with the Ising language, you can think of it as an antiferromagnetic Ising model with both transverse and longitudinal field, because now the longitudinal field does not spoil the criticality due to the fact that it's antiferromagnetic. And then you see at the end of this line, the model can realize a different universality class known as tricritical Ising. And after this, we have simply a first order phase transition. And another thing that I want to highlight about this model is the order parameter. So the sigma field, that in the field theory language corresponds to the spin field, can be related to the occupation number just by this formula. So we have a sort of dictionary between the number operator and our CFT spin operator. And this field is charged under translational symmetry. So you can think of the translational symmetry in this model as the Z2 symmetry that you have in the spin language for the Ising spin chain. And the fact that it's charged under translational symmetry means that if I break translational symmetry, like for instance by putting a boundary, by having some open boundary condition, then I get a non-zero expectation value. Exactly as if I, let's say, break the Z2 symmetry for the Ising spin chain. Okay, so just to convince you that the spectrum that we derived before for the Ising model does not depend indeed on the specific microscopics that we are looking at. Here I want to show some comparison between so the red circle that we saw already before and the spectrum that one can get by simply diagonalizing this Hamiltonian. Here we are choosing a system size of odd length for same boundary condition, or even length for a different boundary condition, like 31 and 30 spins. And here basically, so before for Ising was the parity, no? That somehow could discriminate between plus and plus minus boundary condition. Now it's the length of the system, like due to the symmetries, due to the fact that this Hamiltonian has reflection symmetry, choosing an odd system corresponds to have plus minus boundary conditions, while choosing an even system size corresponds to have anti-aligned, so plus minus boundary condition. And you see a very nice agreement for the between data and CFT prediction. Okay, so now let's come to the experiment. So the way in which they experimentally were able to observe the spectrum is the following. The first step is just the initialization of our system into the disorder, deeply in the disorder phase. So empty, all the sites are empty. Then they perform an adiabatic preparation of the system, meaning that they slowly change the detuning parameter up to the critical point. At the critical point, they apply the tuning modulation. So the modulation takes this form. You see, we have this cosine function that depends on the frequency that they are applying, and applied for a given amount of time. And then we have the operator, which is the total number operator, basically, of the system. So at the critical point, they apply this tuning modulation, and then they run to the order or to the disorder phase, usually to the order phase, And at this point, they count the change in the number of atoms with respect to the ground state. And you can see that this change in the number of atoms can be written as a sum of the excited states of this Gaussian. And so whenever the frequency of the modulation that they are applying coincides with the energy difference between the excited and the ground state, basically we have a resonance in the change in the number of atoms, no? Because it means that this Gaussian basically, like the exponent of this Gaussian is 0, and so this term is simply 1. And this is also proportional to the let's say, to this matrix element of the number operator between the ground state and the excited state. So basically, the technique that they developed allows us to relate the modulation frequency close to an excited state energy to an increase in the ground state population. Now, let me show a bit better what does it mean. So here we have an odd system. So I said the odd system, same boundary condition. And you can see here we have 4 peaks. And each of these peaks can be related to one of the universal ratio of our conformal field theory. Like this ratio here, 2, 4, 6, 8, are exactly the same red circles that I was showing before. And this is for a specific system size, like 23 spins. They have repeated it for different system sizes, like from 7 to 35. And here you see that by just rescaling the frequency time by n, which also confirms the fact that the energy scales as 1 over n, they can see a very nice alignment of all these peaks. So you see this first peak, the second, the third, and the fourth. Now here you see 2, 4, 6, 8. However, before when we were constructing the spectrum, we also saw 3, 5, 7, 9. So what's happening? Like why we cannot see also these spins? Yeah, the explanation is that if you look at this matrix element, basically the ground state is even under spatial parity. The number operator is also even under spatial parity. This means that this matrix element is non-zero only if this state here is also even under spatial parity. So basically, applying this like a modulation containing only the number operator does not allow you to see states which are odd under spatial parity. However, they can change the modulation that they apply in such a way that now this modulation is odd under spatial parity. And so if it's odd, it means that it can couple to an excited state which is odd under spatial parity. And indeed, you see that like these orange lines that they obtain by applying this different parity can, let's say, more or less capture the peaks that we expect for this case. Actually, in this case, it's a bit more complicated because to apply this odd modulation, they are basically introducing a sort of relevant perturbation in our Hamiltonian. This is why we observe these peaks. So we have an explanation for this, but still the results are matched pretty nicely. And in principle, the same strategy can be repeated for plus-minus boundary condition. So for when we have an even system size. And here I report the even states that one can observe in this case. Now, in the 5 minutes left, I just want to very briefly mention that one can also observe the other universality class that we have in the phase diagram of the Rydberg Hamiltonian, meaning the tricritical Ising spectrum. So, yeah. you see, this is the easing transition, and so far we were looking at basically at data taken from this point, so for this value of the dipole-dipole interaction. You can decrease this V2 up to arriving to this point here that basically corresponds to the critical easing point. Now this requires a negative value of V2, which is meaning attractive interactions, while the atoms naturally have repulsive interactions. They are able to access also these this point, but the difference is that in this case, rather than a fixed boundary conditions, they probe a spectrum corresponding to free boundary conditions. And this is also shown by the fact that the one-point correlation function of the order parameter is 0. So basically we are not breaking any symmetry. Or let's say we are not breaking in a relevant way any symmetry of our model. And yeah, I just want to mention that they were also able to basically apply some local fields to the first and the last spins in order to probe different boundary conditions of the critical easing, meaning not only the boundary conditions, not only the free boundary conditions, but also the fixed boundary condition and another intermediate boundary condition that matches pretty nicely the energy ratio between the second and the first even parity excited states. I don't have a lot of time to enter into the details. The main take-home from this part is that also for critical theories different than Ising, they were able to find a good matching between the low-lying excited state predicted from the conformal field theory and the experimental setting. So let me wrap up. I think it was very nice to observe some features that one can study theoretically in a conformal field theory setting in this experimental setting, and they were also able to prove the inverse system size scaling of the energies. That is also pretty nice. Now, what is in our to-do list? Well, we have already some data for correlation functions, for the one-point correlation function, and we are trying to match them with the CFT predictions. It seems that there is a sort of effective temperature in the data that they have, so we are trying to understand better where does this temperature comes from in the experiment, and what they are actually preparing. Once we understand better the correlation function in the pristine easing or critical easing criticality, we also want to use the same set of data to verify measurement alter criticality, meaning what happens if I perform weak measurements on the ground set of critical systems. And for this, recently, together also with Pablo here, we found a way to let's say, probe signature of measurement alter criticality by doing a post-selection on the experimental data whose post-selection probability is not so bad. So we hope that this kind of program can be applied on the set of snapshots that basically we already have for the correlation functions. And yes, with this it's all. Thank you.
Thank you, Sara. So we have time for some questions.
Thanks for the nice talk. So my question is, in the experiments, they used the density modulation because it was natural, but how sensitive is it to the choice of this operator? Like, if I have a different microscopic model in a different platform, how would I know what the correct operator to modulate is?
Yeah, so I think like these this derivation is just based on some response theory and then some first order perturbation, let's say time dependence perturbation. So strictly speaking, I don't think it should change a lot based on the platforms that we use. Now you have to think in terms of the symmetries and this matrix element, whether it's compatible or not.
I see, thanks. And my second question is, so in some of the spectra, like there were some degeneracies, right?
Oh,
How can you resolve that using this method?
Right. So basically, when you prepare this system, but also if you do some simple, mainly when they prepare, there are some irrelevant perturbations that basically lift the degeneracy, and so only one excited state couples to the ground state. So yeah, they are inducing some irrelevant perturbations that don't spoil completely your CFT spectrum, but still they lift the degeneracy, and so they find that only one excited state.
I see, thank you.
Thanks for the nice talk. Yeah, I wanted to ask how difficult is it to do periodic boundary conditions in the experiment? Because I think the current spectrum is boundary scaling dimensions, right? You know, and so yeah, to see the bulk scaling dimensions.
Okay, this is, so I don't know exactly for them how much more difficult it is. I guess it's, I mean, the problem is mainly the system size. I think if they want to use periodic boundary condition, they are constrained to smaller system size, and you see that already for 35, the results are very bad. Because they had basically the probability of losing basically your atoms increases with system size, and so they have to do a much harder post-selection on the set of snapshots that they take, and the quality of the data is very bad. So I guess that for periodic boundary conditions, where you would observe, let's say, all the operator content of your theory, they are restricted to even smaller system size, and yeah, I don't know how good this will be.
Thanks.
Yeah, thanks for the nice talk. So in this absorption spectrum, what determines the line width of the peaks?
So you mean these?
Yeah.
This is a fit. Basically, they fit the experimental data with like here with the sum of 4 Gaussian.
Mm-hmm.
And in principle, we also have some, I mean, from the fit, you can also extract the peak and compare the peak. I think I have a picture for this.
Yeah. And then the width of that Gaussian, is that coming from the pulse you're applying or from the second adiabatic ramp, or do you not understand yet?
I think it should be related to this omega parameter here.
Okay.
Which fixes this Gaussian envelope in the modulation that they are applying.
Okay, so it's dominated by that Gaussian envelope right now. Okay. And then like a broader question is, do you have thoughts about measuring operator product expansion coefficients in some of these platforms?
No.
Okay.
Honest answer, no.
The vertical lines are coming from fitting, or a priori you know where they will be?
This vertical line here?
Yeah.
These are just CFT predictions.
Yes.
Yeah.
I think it's along the line of the first question. How do you know that matrix element is not going to be 0 a priori?
So
all of a sudden, some of these could be just absent, no? How do you know this is going to not kill a peak? I mean,
so these, so we have done some numerical computation for these, and it seems to be roughly constant in the system size.
But I'm saying an unknown model, you take it, then a peak could be just missing because this matrix element just becomes 0.
No, indeed, I think I mean, this formula holds. The point is, one has to check whether this, I think this is the caveat, like if this matrix element is 0 or not. Yeah, I think this was my question. This I don't know.
Yeah, thanks for a very nice talk. Maybe a naive question. So is a claim that these like collapse only happens if you're at the CFT, or like can they accidentally happen? And also like what happens if you perturb the Hamiltonian to the spectrum? If you're not exactly at the CFT point, but maybe you're close, and if you move closer, like what happens?
I think it depends on what do you mean by close, like in the sense that if you have an irrelevant perturbation, maybe we would expect some slight deviations from what we have, but then if you have a relevant perturbation, maybe this can drive you to a different fixed point, and then or it can gap your Hamiltonian, and then indeed it would be very different.
Okay, thanks.
Yeah, thank you for this nice talk. I guess I also have questions about understanding the plot as you are scaling the system size up. So it seems to me the quality of data is actually much better at a smaller system size, and you also already have all the peaks there. I'm just wondering what we learn more after you're scaling the system size up. How should I interpret the data?
Oh, because the energy, you see, like the energy decays as 1 over n.
Yeah.
So
you want to say?
So we want to basically align all the peaks.
So you already rescale your x-axis for that plot?
Yeah, we rescaling.
That makes more sense. I see.
We were rescaling the x-axis by the frequency by n in such a way that all the peaks align.
I see.
And about the system size, yeah. So it's true that from 19 to 27 there are no huge differences. But for instance, 7 is still too small to observe the peaks. And as I said, 35 is too large.
Yeah,
because,
maybe the density become clouded, you have many heating effect, maybe, I don't know. Okay,
so because as far as understood, the probability, the decay probability of the atoms increases with system size.
Sure.
And since they do some post-selection on the snapshots that they get, basically the remaining snapshots after this erasure detection that they do is very hard. Like they lose a lot of data, basically.
I see. Sure, thanks.
So could this be done in higher dimension? And are there any prospects for learning about higher dimensional CFTs?
Yeah, higher dimensional CFTs. This is an excellent question. Let's say if we convince Manuel to do it, then it would be very nice. Yes, but I think there are still a lot of information that one can extract only from this set of data, like correlation function, ratio of correlation functions, velocity. I mean, we are still trying to understand what is the maximum amount of information that we can extract. And yeah.
And also, I guess you could get entanglement out of the existing data set, probably, or
not yet, I think.
Because your measurements are not complete, right? You're just measuring.
Because
occupation.
These are only measurements of the occupation
That's
number.
Right.
I don't know how to reconstruct the entanglement from that.
You have some more questions? Yeah, maybe I'll ask a last question then. Can you explain again what those intermediate boundary conditions
were? Oh, yes.
were?
Thanks, Federico. Indeed, so let me tell you first theoretically what's happening. So if you have your system tuned to the critical easing point, even though in principle you break translational invariance, if you don't apply any, let's say, boundary field, you are naturally realizing some free boundary conditions, because for the critical easing, free boundary conditions is a stable fixed point. So you have a stable fixed point when you don't apply any boundary detuning. If you pin your spins, then you flow to some fixed boundary condition, which is also a stable fixed point. So between these two stable fixed points, you have an intermediate fixed point that basically you can realize by simply changing the strength of the field that you are detuning. So basically what they do is they change this parameter eta from 0 to 1, And they find that for eta equal to 0.39, if you look at the spectrum, you see that the ratio between the second and the first excited state is compatible with this specific point in the BCFT spectrum of the tricritical easing, which is called 0+ boundary condition. So it means that if you have a 2D model, you are not completely pinning your spins at the boundary, you are partially pinning your spins at the boundary, so you are not implying, let's say, a huge magnetic field, you are applying a small magnetic field, and this is what's realizing this intermediate fixed point.
I see. Thank you. So let's thank Sara once again.